Hey, looks like we're up and running. I'm going to try to keep my comments to a minimum and just get some practice with these 11 problems again. Let's get this so that I can see everything. All right, so get an x-axis. The one is not there, but it's a first degree term. And so we're going to get a sign change at 0. We're going to get a no sign change at 3. And we're going to get a cubic root at -4, at least what looks to be a cubic root. -4. And now if I put a million in, I can see that I'm going to get a negative, a positive, and a positive, and that product is negative. So this is what the graph looks like. A little bit of a cubic look there. Right? And we want to know when we're less than or equal to. So I can see that I'm equal at -4. Less than or equal to, well, let's just write the answer the way I see it rather than try to explain anything. So from -infinity to -4, and -4 works. So that gives me all these negative y values. And then I get positive y values out of these x's, so these do not work. And then I pick up again at 0, and 3 does, so I can simply say 0 to infinity. Can't bound infinity. All right. Let's see if I can get this off the board. Should have had that erased before. Okay, let's do this. I had started this video earlier. Had to start again. Phone call. So there's some writing on the board already, but let's get cosine function. Max to max is the simplest way to do it. You get 0 here, right? This is where we start measuring circumference distance. And when we get all the way around, we're at 2 pi. So if we want one period, then we want the parentheses to equal 0, and we want it to equal 2 pi. It's that simple. The range, midline, I'm talking about this now in other videos. 9 going up 7 takes me to 16, down 7 takes me to 2. And I'm going to start here with setting this to 0, which happens at 5. And I know if I divide 2 into pi, my period's going to be pi. So this is going to be 5 plus pi, bringing me back to 16. This one gets me 16. And now I really own this thing. So 5 plus pi over 2, you might want to put this input to see if you are seeing the calculation correctly to get 2 as an output. And you can put more values on there. Let's do one sine function here. Now the sine function, positive sine function, starts at the order. It doesn't start, it's just no problem. No number is really more important than any other, but it's easiest to work with 0. So the sine function is about heights, and the height here is 0, pi over 2 it's 1, 3 pi over 2 it's -1. So we're going to start here. But instead of a positive sine function, we've got a negative sine function. So that's the shape. And I want this to equal 0, and I want it to equal 2 pi. And look at x over 8. X over 8 is 1/8 times x. If you can always isolate that multiplier, you can find the period by simply dividing by that multiplier. So I know this is going to end at 16 pi now, just by looking at it quickly. All right, in the middle is 11, so that's 11, and that's right across the board. So this is going to be 5 less than 11, so this is going down to 6, and this is going to be 5 more than 11, going up to 16. All right, and so 0 gets me 11, and now I've got all kinds of symmetry. 8 pi gets me 11, 4 pi gets me 6, so on and so forth. And as long as I'm not making a mistake while I'm talking, then that should be okay. But I usually do something stupid somewhere in a video, so we'll see. You want to factor x squared minus 9 to be x plus 3, x minus 3. Then you're not allowed to divide by 0. So we got a problem here at, I'll put a little open circle at 3. We got another little problem here at -3. Actually, I kind of like this because it looks like what you study in earlier grade school for intervals. But we'll convert it to interval notation in a moment. -7 is okay. -7, that's your domain right here. In a method that you practiced earlier, but putting it into interval notation, we have -7 to -3. Can't use -3, but we can use -3 to 3, but we can't use 3, but we can certainly take it from 3 to infinity. And that's interval notation. That's the domain of that function. And the domain is, what can I plug in so I get answers out? You can plug these numbers in and you'll get answers out. All right, rational functions. Tons of these on the internet. All you got to do is, if you're looking for practice, is you probably get these types first. Sketch or graph. Rational functions. Go to YouTube. Get all the practice you want. Okay, so I'll just graph this quickly. I can see -6/5 is my y-intercept. So -6/5 is that y-intercept. -5 is going to give me some asymptotic behavior. I can see that this is going to go to a height of 3 when I put big numbers in. I'm getting close to 3. Let's put 1,000,000 in. 3 million minus 6 over 1 million plus 5. I don't think these little guys affect that ratio too much. It's a 3-to-1 ratio. And if I put -1,000,000 in, I'm going to get the same thing on the end behavior on the left. The bigger the number, the bigger the negative number. Should I say the smaller? I always wondered about that. The magnitude, certainly. The bigger the magnitude of the negative number, the closer the ratio is to +3. Why did I write negative? I corrected it. Okay, x-intercept. Yeah, there is one. I hope you can see that it happens at 2. All right, so now I can see the trajectory right there. And if there are no other x-intercepts, there's only one way to make this 0, and that's 0 over some number in the denominator. So no x-intercepts, then it's got to look like that. And I think it's important that you plug in a number like -5.01 into that equation to see that you're getting movement towards infinity. That's on you. Plug it in and find that out. So when am I less than 0? Well, I can see it now from this x value, -5, all the way over here to 2. All those y values are below the x-axis, so that's when I'm less than 0. Domain, well, I can use everything except -5. Range, yeah, you can do range from -infinity to, not sure you can see that, from negative, you can see the graph, so from -infinity all the way up to 3. And then from 3 all the way up to infinity. Okay. Now, asymptotic behavior here doesn't mean I can't have the number 3 somewhere in the graph, but in this instance, I can't. But in some other situation, asymptotic behavior is really all about the extremes. And what can we say? We can say one thing: your x values aren't changing here much at all. They're -5, but the y values are changing immensely. But that's why x equals -5 is an asymptote, because at x equals -5, there's a lot of change. Y equals 3 is an asymptote because I can put in all kinds of x values and I'm getting the answer out close to 3. I hope I did justice to that cause. What do I see here? I see a tricky one. Be careful. Be careful with this one. Get the y-intercept first, -6/9. Okay, so we'll call that -1, -6/9, right around there. But then after you get the y-intercept, you should factor these. 2 times x plus 3 over x plus 3, x minus 3. Now I hope you can see why you better factor all these things. So what we thought might have been at -3 an asymptote, that all that numerical activity just got canceled out of the problem, divided out of the problem. But it doesn't change the fact that -3 is a domain restriction. I cannot put -3 into the original way I wrote this. Right? I can't put it in here either, because if I do, I get division by 0. So -3 is a problem. We'll come back to it. We'll come back to -3 after we graph 2 over x minus 3. Now what happens as the denominator keeps getting bigger and bigger and bigger, and two stays the same, unless you see this change, I think it's constant. And if you do see it change in the next 30 seconds, again, I told you this before in other videos, write to me. Let me know where you are. And we'll chat a little bit. See if we can, well, you can guess where that's going. All right, so y equals 0, right? Again, 2 divided by 1 is 2, divided by 10, divided by 100, divided by 1,000. I hope you can see it's going to 0 on this side and this side. Okay, x-intercepts? No, we don't have any x-intercepts. There's no way to make this, we're back to that conversation again. I can't turn that into the number 0. There's no variable to work with. So therefore, there is no x-intercept. And we do have an asymptote of 3. Okay, so positive 3. And if I put a really big number in, I get a positive, so it looks like this on the right, and therefore it's got to look like this on the left. But again, one more thing to think about, negative 3, can't use it, but I can use it here, and that's 2 over negative 3 minus 3, which is negative 1/3. And we call that a point of discontinuity. So over here, I've got to you remove that data point at 3, negative 3, and you want to show that to the reader that that data does not exist. And I think I've labeled my asymptotes. Don't think there are any x-intercepts. I've labeled the point of discontinuity. We can move on from that. You got a little practice there. All right, so what do we got? We got the absolute value of 0 is the smallest distance you can travel. That's going to stay put. Negative. I know that 5 gets me 0, and 0 times anything plus 9 gets me 9. So that's the vertex. I actually can look at this and say I'm traveling up at 6 to 1 on this side, moving up at 6 to 1, and I'm coming down at 6 to 1 on this side. We can prove that with a y-intercept. Let's get the y-intercept over here. At 0, comma, what do we got there? Negative 30 plus 9, negative 21. How far is it from negative 21 to 9? 30 units, you say. How far is it from 0 to 5? 5 units. Oh, yes, that's a 6 to 1 rate of change. I guess the multiplication there tells me the slope on the branches. So I'm going to write my piecewise that way today. I'm going to use the vertex and the multiplication so I don't have to write quite so much. So let's get Alfred Hitchcock on the board. And so my y, h of x, sorry, I'm calling it h of x, could be written as positive 6 times x minus 5 plus 9, which is what you get if you multiply this out, and negative 6 x minus 5 plus 9. I guess that's the one you get out of multiplying it the way it's originally written. And I'm only climbing at a 6 to 1 rate until I get to 5. So therefore, less than 5 is what I'm climbing, and decreasing greater than or equal to 5. And those are the pieces. So we got our sketch, we got our piecewise. When's this equal to negative 15? Well, 0 got me what? Negative 21? It's nice to know that because negative 15 is here. All right, so, probably at 1 or 2 units doing these so that we have integer-friendly values. So probably around 2, 1 or 2. If I don't get that answer from the first branch, then I made a mistake here conceptually or numerically. So let's solve this quickly. You can see everything all right. So that's minus 24. That's minus 4. Add 5. That's 1. Okay, so we're in good shape. Now, if I want to shortcut this problem, if that's 1, and I know over here a 10 gets me negative 21, then I know 9 is my other answer. Okay, but let's find it. So what equals negative 15, x values 1 and 9. Let's prove that 9 works. So let's do the second branch, negative 6. Subtract 9 minus 24. Divide by negative 6 gets me positive 4. Add 5, there's our 9. All right, so there are shortcuts to all this. And the shortcut graphically is right here. What do I want? I want it greater than negative 15. Well, that's the top part of the graph, so my answers are from 1 to 9. You use any of those numbers and you're greater than or equal to negative 15. So x's could be less than or equal to 9, but they have to be greater than or equal to 1. Now, what is the way that we did that? If you didn't follow what I just did as a shortcut, then you get a number line, you put your answers 1 and your answers 9 here, and you just try numbers and find out if it's true or false. I'll put 10 in. All right, so that's minus 30 plus 9. Well, we already knew that. That's minus 21. If I put 10 in, I get minus 21. Is minus 21 bigger than negative 15? Heck no. Right, and these change. So that is going to be a yes, and that's going to be a no. Right. False, true, false is quicker. Okay, so 1 to 9, that one's done. So all kinds of ways to write these sinusoids. I think the easiest to understand is the sine function. So when you get a -1, 3 pi over 2. All right, so do we want to base it off of that? I think so. Let's do it. So what do we have here? We've got the middle, which is 50, going up and down 10. I'm going to go down 10 if I put 3 pi over 2 in there. So this is sine function. What do we have? 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. 5 pi, how many years did it take? 2024, 24 years. I am going to put this in a that spot. X minus 2000. And I want to get -1 out of this, which will make -10 plus 50, 40. And that happens at 3 pi over 2. So why don't I just include it right there? Okay, so the sine, when I put 2000 in, of 3 pi over 2 is -1. That's 10. -10 plus 50, there you go. All right. If I want a -1, well, pi does that on the cosine function. So we got 50 plus 10 cosine. And now all I have to do is the 5 pi over 24, x minus 2000. I'm going to have to erase this one. Plus pi. Okay, so you put 2000 in, you get pi. What's the value at pi? Pi radians, 3.14 radians. -1 is the width. Cosine's width. There's your -10 plus 50. And you got that one. Now, textbook would probably do this as a negative cosine. So I'll do it the way a textbook would probably come your way. Because they generally just work with the cosine function. Because at 0, you got a max of 1. At pi, you got -1. So if we create the number 1, in this case, we want y equals still the center 50. I should have written that over here, right? And in this case, we'll go down 10 cosine 5 pi. I don't even think they do it that way, but it's easiest to do it this way. 1, 2, 3, 4, 24. That's right. Forgot that. X minus 2000. And that's another way to write it, probably more succinctly. But learning it, I don't know if that's the best thing for you, but it doesn't hurt to come at it from different perspectives. Okay, if I made a mistake, I'm not catching it because I'm not really checking my work too much. So 45, I know 45 is 9 times 5. I know 9 is 3 squared times 5. I know 3 is e to the 1.1, and we're going to square that. And I'm going to multiply that by e to the 5, 1.6. So what are the exponents that I'm putting on top of? E to get 45, 2.2 plus 1.6 looks at it's approximately 3.8. Now we'll do it with the rules of logarithms. So I would say that the ln of 9 times 5 would be the start, which gives me the ln of 9 plus the ln of 5. And then I have to create the ln of 3 squared plus ln of 5. And what am I doing to the exponent on top of e that gives me 3? Well, there it is. I'm multiplying 2 times 1.1, which means I can put this 2 in front of the ln. It's going to take you a while to see how this works. But that's how you can do it with the rules of logarithms. So there's your 2.2, there's your 1.6, and there's your 3.8, just using the rules of logarithms, which is really all about, I hope you can see the addition of these logs when you're multiplying. I suppose I should put it over that. Hopefully you can see it. I don't want this thing going on forever. Trying to get some quick practice with these problems. All right, so when you're graphing logs, you want the parentheses to equal 0. What makes that parentheses 0? It's undefined when you use 8, it's undefined because this parentheses has to be positive, and our positives start on the right side of x equals 8. So my graph's going to appear on that side. So it's kind of like a domain restriction. All right. When does it equal 1? 9's important. And when does it equal the base 8 1/3? So I'm going to move the 9. I'm going to do this one first. So if you put 8 1/3 in, see if you can do the math. 8 1/3, and you'll find there's a nice shortcut. Yeah, 4 plus 5 is 9. So 8 1/3. 8 1/3 gets us 9. And we're going to find that it does this. And maybe I'll try to find a coordinate here where you can see the asymptotic behavior. Okay, but right now we're going to get a value here. When I put a 9 in, 9 minus 8, I'm going to play with it right here, is 1. And I hope you're getting to the point where log 1, doesn't matter what the base is 0. 0 times a multiplier is 0, and you're always going to get, when you put a 1 in, you're always going to get the constant. So that's 5, and 5 is smaller than 9. That 9. Right? The 9 we just picked, I forgot. Oh yeah, that's what got us the 1. So this 9, I hate the same number showing up anywhere when you're first learning something, but it is what it is. Not going to do the video again. Okay? But 8 1/3, well, how about if you used 8 1/27, for instance? 8 1/27 minus 8. Well, that gives us 1/27, and maybe now you know why we did so many of these problems at the beginning of the semester. 1/3, that's going to be A3, right? 1/3 cubed gets us 1/. So that's 12 plus 5, that's 17. So I'm hoping you get another value here that's getting closer to 8. And if I made it 1/81, that's even closer and a bigger number. Okay. Sine of negative 17 pi over 6. God, I hope I had this up high enough. I hope so. Circle. Chunks of 6. Which means that minus 12, oh, going this way. Minus 12 pi over 6. To get to 17, I need another 5. Okay, and that's going to put you here. Take your time. X-axis, a little 90-degree. Hypotenuse is still 1. Sure looks like that's minus 1/2. And that's the sine function, is all about the heights in the unit circle. We're done. Well, I took a lot out of me that time. All right.